out, see if it actually works. With hydrogen NMR, again, go through it simply. The number of signals first. There's 2 signals, which means 2 types of hydrogens. Okay? Chemical shift. Where do those hydrogens show up in their ranges? Start to do some interpretation about what atom is attached to that hydrogen. Integration has to look at peak height is one way you can approximate. I have seen the ACS study guide make reference to peak height. In general, that is a bad method because what we're looking at is counting hydrogens with that specific chemical shift. Okay? If we have a hydrogen that is very reactive, say like an acidic hydrogen, those hydrogens, or within a sample of that molecule, okay, each of those hydrogens will have a very drastically different chemical shift, because in one case, for the carboxylic acid, it's attached to the acid. In the extreme case, it's not attached at all. That changes a lot of its chemical shift, because it's either attached or not. That means as far as where NMR decides to record that signal, it's across a very broad range. It's still just one hydrogen within the sample. Okay? So peak height is usually a bad thing to do. You want to look at the integration, which is the area underneath the curve. At least within the study guide, all they're really asking is based on peak height. So you can do some quick approximations in that situation. So in this case, if we take a look at our peak height, it's roughly 2 to 3. Okay? That gives us the ratio of hydrogens present. So our shorter peak is roughly composed of 2 hydrogens, and the taller peak is probably composed of 3 hydrogens. That is a ratio, so it could be 4 and 6, or it could be 6 and 9. So I do the math. I think I did that right. Okay? After that, we can then bring in our multiplicity. Okay, so here's your full spectrum. All of that information is on there, but remember, try and zero in at each of those small steps along the way and only see that information when you first interpret it. Okay? If we jump directly to the multiplicity, that is where mistakes can be easily made. Yes?
If they show a peak for the solvent, will they label it?
Good question. I don't know if they will label it or not. For hydrogen NMR, chloroform is your standard solvent. I doubt they would put anything else in there. Chloroform shows up at 7.27, I think. The other signal that might show up would be what's labeled on here as TMS, tetramethylsilane. That is a 0 value. So it's added to make sure we have a 0 on which to compare everything to. Without that, we don't have a chemical shift range. Okay, so what we're looking at is the shift away from that standard, which would come into play with our chemical shifts values. Okay, with our multiplicity, the rules there is it gives us the number of neighboring hydrogens. Only works for hydrogen. The neighboring hydrogens, we're looking at our number of peaks. The number of peaks equals the number of neighboring hydrogens plus 1. So if you see 3 peaks, that means 2 neighbors, okay, which is the standard way of going through and interpreting. You'd look at the number of peaks. Deciding how many peaks there are, okay, how many peaks do you think there are for that? I know first is kind of a stretch, but that first one, how many peaks are there? 4, and the next one? 3. Some people can see that easily, some people can't. Really the only way that you can get that to the point where you can see it consistently is practice. If you don't have that practice, ignore multiplicity and hope you can figure it out some other way, okay? Which you probably can, yes?
If there's only 2 signals, would you assume that they're neighbors with each other? Or is that?
If there are 2 signals that are split, yes. Then yes, they would be neighbors to each other. They would still have to split. Okay. A neighbor is defined as less than 3 bonds away. So there are structures where we have hydrogens that are different from each other attached to the same carbon. Okay. The classic example is a terminal alkene. Those hydrogens, in fact, all 3 of those hydrogens are now different from each other. So all 3 of them should have a unique chemical shift. How different that chemical shift is an entirely separate issue. Okay, but all of those chemical shifts are different, so we would expect to see 3 sets of signals, okay, 1 for each of those. And we would see that neighboring split effect as well. Okay? Shoot. Oh, other big effect with multiplicity, which is probably more important or easier for interpretation. If you have a nitrogen or an oxygen, they will hide hydrogens. So if you have an alcohol group, so let's erase that for the moment. Say we put an OH here. If we count out our bonds, this is 1, 2, 3 bonds away. These 2 are within that 3 bond rule. They should split each other. They don't, because oxygen kind of gets in the way and prevents that splitting effect. So if you have nitrogen or oxygen in your structure, they hide hydrogens. You will not see a splitting effect with those.
The electronegativity.
I'm not sure the exact rule on it. I would go something between those, electronegativity or probably electronegativity.
So no peak at all?
Not no peaks,
Okay.
because the hydrogens are there. They will get counted. There's no splitting of that peak. So with each of these things, we look at the number of signals, every single hydrogen gets counted. We have those signals show up. When we move to the chemical shift, they will get counted or categorized according to their what's closest to them. So that's looking at, say, a nitrogen or a carbon or an oxygen. Then we look at the integration. If there were multiple of those hydrogens in that position, the peak gets bigger. Then we look at splitting or multiplicity, and that's, are there neighboring hydrogens? Well, if nitrogen and oxygen hide hydrogens, then they won't see each other. They can't do the splitting. It still gets counted. Okay? Kind of makes sense. So that's kind of your quick and dirty for everything. So let's take a look at an example, because let's see. That was bad. I can't go back now. I think we'll take a look at that last slide as an example.
I think we'll go back and eat some more pizza.
Yeah, feel free to get pizza whenever you want. You don't have to wait for me. So we don't have the mass spec here, which makes this one a little bit more difficult. And I'm not about to wing out what the mass spec information is. So we'll see if we actually need it. Maybe we don't need it. So we'll start with the IR. What do we see in the IR? CHSP3s. Do we see anything else?
Is that a 1700 feet? Or is it
That line is 1500. So what does that mean?
Everything else in fingerprints? Not
Everything else is really in the fingerprint. I wouldn't touch it. So carbon NMR. How do we know that's carbon NMR? Hmm?
No area under the curve?
No splitting, no area under the curve. Both of those are valid. Say there's a bigger thing. Look at the chemical shift. Okay, your chemical shift for carbon NMR is 0 to 200. For hydrogen NMR, it's 0 to 14. Okay, so as long as we clear 20, we're in the carbon NMR. So where do those signals show up? 0 to 40. Pretty sure these become alkanes. This guy, I don't know. Okay, so the standard range to remember for our carbon NMR, I think it's 0 to 50 is our alkanes. Then it's 100 to 150 is carbon-carbon double bonds, either aromatic or alkene. And then about 200 we see carbonyls. Okay, so I would put a question mark there. The next thing I would also add is that I've got 4 unique carbons. Okay, so I've got that little bit of extra information. The next part is approaching your HNMR. Okay, and this is where it can become a little bit more difficult. For sure, I've got a group here and a group here. What's going on in the middle? A lot's a good answer. It's a difficult question.
Could be 2 groups together.
It's probably 2 groups, 2 separate things. The reason being is that when we look at our splitting pattern, we split symmetrically. That's not symmetrical, which means there has to be at least two things in there. What I see is that we see two peaks very, very tall next to each other, and then I also see a bunch of smaller peaks hidden down underneath. Okay? So I see two sets of hydrogens. Okay? So total, I've got 4 unique hydrogens.
What's those little notches at 2.5?
2.5, those guys.
Yeah.
Too small to see, so at a first pass, I would say they aren't there. Okay. You can get noise showing up in the NMR. These ones were digital, so they should have come up clean. The ACS test probably uses digital ones as well, so they will probably also show up clean. Actually, now that I look at it, I do know what those are. Those are satellite peaks. If you get a signal that's really, really, really intense, sometimes what can do is it can double. So what we've got on those 2 purple peaks are a doubling of our 2 really tall peaks. Okay, it's a satellite peak. I don't know the physics behind that or why it does that, but I do know it does happen every so often. I really don't have an answer beyond calling them satellite peaks. You would fully expect to see those over here as well. The problem with not being able to see them is it's underneath a different signal, so we can't see that. Okay? So you can see the satellite doubling effect going out either direction. So 4 unique hydrogens, not a whole lot of information there. We could look at chemical shifts. Most of those are in our 2 range, which says we're looking at alkanes. This other guy is in what I would call a dead zone, so I wouldn't analyze it as far as the chemical shift. We could then go through and look at integrations. Awesome, they somehow did not make it to the slides. Which is where we would then have to kind of approximate with this based on the heights. Okay, so the 2 tallest, probably looking at what integration as a guess.
4.
How easy is it to get multiples of 4 or get 4 hydrogens all the same as each other?
Okay, so not 4.
Right. Well, and so that's a lot of what NMR is looking at is it possible to do that? It is absolutely possible. We can do that. But that's probably a little bit more difficult than we'd want. Okay.
3, 2, and 1.
3 probably makes the most sense. That's the largest we could get, and get methyl groups. Okay, and then we could continue our structure outwards. So I would probably call those 3 integration. Nothing to do with the number of peaks. This is, nope, integration. How tall are the peaks? So what we're doing is now comparing the intensity of each of these. Okay, so I would probably try 3, 2, 1, and 1. Trying to remember what the structure of this was.
That's the ratio, basically.
That's the ratio of those signals. Okay. And this is definitely a harder one. I think your 4 might actually be right. Really hard to do without the integration information. On the test, what you're going to see is a litany of possible options. Okay? So hopefully you would be able to eliminate a decent chunk of these and be able to get your final answer based on that. Without that, what I would really push you to go through and do is address each of these things on their own and try and work your way from there. Without solid integration information, that's going to make looking at the splitting difficult to interpret. Okay, but we can go ahead and give that a shot. The signal that we're calling 2, so I'll label that as 2, has what for a splitting pattern? How many peaks? 3 peaks, which means doublet means
split by two neighbors.
So it's two neighbors. So what we can go through and say is that we have a hydrogen attached to a carbon. How do I know it's a carbon? It was in the alkane range, and that is likely attached to another carbon. Why does it have to be carbon? Splitting. It's split. So if it's split, it has to have that carbon with two hydrogens.
Is this the structure, or is this the IR and everything of it?
Yeah, that is the right one. I don't think those integrations are right either, though,
Okay.
in all honesty.
So the only,
We then also have a signal at 3. We really can't interpret much more than that. We took a guess and said that there were two hydrogens there, so we could say that our hydrogen, that there was another one here as well. Because I don't trust that integration information, I don't want to put that information down, because ultimately what I'm doing is guessing and then trying to base my answer off of a guess. That's going to be pretty questionable. Okay? Our 3 signal has what splitting pattern? 2 peaks, which means one neighbor, which means I expect to have, again, a hydrogen with a carbon, and next to it I should have another carbon with one hydrogen attached to it. The rest of those bonds cannot be hydrogen. Same deal up here. Okay, and since I don't know how many hydrogens there are representative in each of these, I won't put the hanging bonds on the first carbon for these. I then have 2 signals that are at 1. We'll call that 1 at 2. We have a hydrogen bound to a carbon.
Is it 3 peaks? 2 neighbors?
And now trying to interpret the number of peaks. Not easy to see. I see 1, 2, 3 peaks. But remember, our splitting needs to be symmetrical. Okay? So I could see 1 shorter, and I'd have 5. The other option, though, was that these 2 were on top of each other, and I might expect to see a peak floating out there. Okay? I don't see that, so it probably means that we're looking at a 5, where that's our tallest, shortest, and the next one down. So we've got 5 peaks, which means 5 peaks, 4 neighbors. How do I get 4 neighbors near my carbon hydrogen? We could look at a CH2 out either direction. Is there anything else we could do?
Well, you can go 3 bonds, so.
We said 4 neighbors, right? Or a CH. This becomes a bit dicey, right? We have 2 possible options to explain that splitting pattern. Okay? This is why it's really nice to have multiple choice. If you were expected to draw a full structure from the get-go, you would have the integration information. Okay? So at this point, we now have 4 pieces that we consider within our structure. Match them to your structures or to your possible answers and see how they match up. Okay? Sometimes they work really well, sometimes they don't. You just kind of have to see what's there and work with it from that. Okay? Would have been nice if we had one with the integration information. Do any of the other ones have integration? Don't. That one does. So let's take a look at this one with integration information, because that'll help out. Whoops. Call this red, and we'll call this guy blue. Red, what information do we know?
Who's in the alkane region?
I would argue you know something before that.
Is he unicarbon?
There's a hydrogen. Okay. We know it's in the alkane region, so it's a carbon. What else do we know about it? What's the next piece of information?
yeah, that's 2, 3.
We know the integration is 3. The easiest way to get 3 hydrogens all the same is to have it attached to the same carbon. What's the next piece of information we know? 3 peaks, which means, 3 peaks, which means 2 neighbors. Okay, that's all that tells us. Okay, so our red one doesn't identify that we have or that those hydrogens exist yet. That those hydrogens exist based on our interpretation. If our interpretation is correct, what should we be able to find in our IR or our NMR? A signal that represents those 2 extra hydrogens. Okay, so if we go back and take a look at our blue hydrogens or our blue signal, what does our blue signal tell us? There's a hydrogen. What else does it tell us? Probably push to saying it's a carbon.
Oh, it is above 2.
It's a little bit above 2, which makes that a little bit more difficult to do, but you could say it's carbon. What's the next? Which means 2 hydrogens. Right? We have 4 peaks, which means 3 neighbors. What's the easiest way to get 3 neighbors? A CH3. Okay. Same idea. That signal does not tell us that there's 3 hydrogens. It's our interpretation of that signal. Does our data match each other? Yeah. One signal says I've got a CH2. I do. One signal says I have a CH3. I do. Okay. That is all our HNMR tells us. It doesn't tell us how those pieces are connected, if they're even connected. It just tells us that those 2 pieces are present. That's where you would have to go through and use IR and carbon NMR sometimes to figure out the rest of those pieces. Okay? So identify your pieces, write the information down as best you can, as quickly as you can, and see if it matches something. Okay? If it doesn't match something, that's helpful too. Eliminate that answer. Move on. Okay? So I know that wasn't a lot on spectroscopy. I mean, as far as time goes, that was quite a bit. But I would say for the amount of questions that you'll see on the test, you don't need anything more than that, other than practice. So if we were going to try and full solve this, we'd have to go through and look at the other stuff. What does this signal mean? Carbon, oxygen, double bond. What do these signals mean? Alkanes, there's 2 of them, 2 carbons. What's our IR show? So the only information we've got is that we've got CH2, CH3. Those pieces look the same, so we might say that we just duplicated it. And we could then combine that with our carbonyl. So we have a CH3, CH2, carbonyl. How many bonds does that carbon need?
4.
What's it attached to? If you make it a hydrogen, what type of bond do you have? What functional group do you have?
Aldehyde.
You have an aldehyde. The aldehyde shows up, which isn't there, so it can't be hydrogen. What were you suggesting?
CH2, CH3, the sentiments on the other side.
There's probably symmetry in the molecule. So if you ever run into a dead space, it's probably symmetry, double, see what happens.
That's what I was wondering, isn't the symmetry, it just intensifies the peak, it doesn't do anything else?
It can't intensify the peak. Remember, it's a ratio. Our ratio was 2 to 3. That could have been 4 to 6, or that was 4 to 6. It's all relative to that other signal. So since there's nothing that's a signal of just one, you can't say it's relative and the intensity gets taller. It doesn't. Okay, the signal at 1 is relative to the signal at 2.5. In fact, when we run the sample, you're probably looking at thousands of hydrogens at the signal 2.5 and thousands of hydrogens at the 1 signal. The ratio of those 2 gets you to 3 to 2.
There was a question on the sampling sample stuff, talking about carbon NMR, talking about DEPT.
that means nothing to me.
Yeah, it didn't mean anything. It was question number 62, if you wanted to look at it. I guess the real question is, do we need to know that, you think, for the test? It was talking about identifying the difference between a methylene and a methylene by looking at carbon and MR. The DEPT stands for something.
I'm pretty sure it stands for something. I would agree with that.
Yeah, Department of.
What was the letters again? D-E?
PT, just like
PT.
department.
I think what that is a second or a different type of carbon NMR where you can get some splitting of the signals depending on the number of hydrogens around them.
Yeah, that's what it was talking about, but that's not.
I've never seen that on the ACS
Okay,
test.
that's.
It is relatively new technology or new information, so you probably won't see that. Other questions? Has anybody looked at the review slides? Well, that makes me feel warm and fuzzy. Are you saying you've looked at the review slides?
I did.
Oh, okay. Or you had actually had a question? Oh, okay. No, that's good. I'm hearing lots of questions on substitution reactions, so I do kind of want to get to those so we can jump through some of this. Your acid-based stuff, a lot of that's going to be resonance-based. Okay. Look for charge. Look for atom effects, so electronegativity and size, and then look for resonance. If you got to keep looking, then you can go for inductive effects, and if you really got to keep looking, that's where you can see hybridization, maybe some solvent effect stuff. It's probably not worth the time to actually look at those, okay, and just guess. With your resonance and mechanisms, what are you moving every single time? Electrons. Please do not move anything other than electrons. Okay? Move the electrons, draw the result, see what happens. Okay? The mechanism can get you through the problem. Some of the things that are really causing issues I've noticed would be anything with rearrangements, so carbocations can be a bit dicey to get through. So draw it. Draw each of those possibilities and make it look ugly as all heck. It doesn't need to look pretty. Okay? Always move your electrons, remember your definitions, and you should be okay. When it gets to a mechanism, you're not allowed to exceed the octet, so you will break bonds. Break the pi bond first, then break your sigma bonds if you need to. Yeah?
You know if there's going to be those sigma complexes?
It's hard to ask a multiple choice question about sigma complexes. Okay? The question that you would get might be, where does the electrophile substitute? Well, really to know where the electrophile substitutes, you're supposed to know all the sigma complexes. And that's why it would substitute there. Or what you could have done is memorized that's a deactivating group, so it goes meta. Okay? So you can get a lot of memorization things out of, or use a lot of memorization things to avoid having to draw out mechanisms like sigma complexes.
They have some questions asking which intermediate explains why substitutes have like para or
So
para or something.
that's the last way that they would go through and do it, is they'd say, of these structures, which of these is a valid intermediate for this reaction? And so, yes, you could see sigma structures show up that way, but I would argue you'd see the same mechanism thing for all possible reactions. So it's not calling out specifically sigma structures. And even with those, if you know it's a deactivating group, where's it supposed to substitute? Well, it needs to be meta. That should eliminate at least 2 answers. Okay. And then between that, look at those 2 structures and say, which is the best looking structure? Because you've now eliminated half of your choices. The correct answer should be the best looking. Okay.
What constitutes best looking?
Stated. So when you look at, say, a sigma structure, whoops. Let me just draw one for real. That's not helping me to just try and guess. if we're going to draw out best looking, the first thing that you need to identify is what makes it bad. So what makes this structure a bad thing? Charge. So look for that charge. Is it a stabilized charge? Is it destabilized? What things are good about it? What things could be made better? So in this case, you should zoom in on that positive charge and say, okay, what kind of positive charge is that? It is on a carbon, so that's not horrible. We've seen positive charges on carbon. And it is a secondary carbon. Our secondary carbon's super stable. Not super, okay? Typically, if you see a secondary carbon, the thing that you should be thinking is resonance and rearrangements every single time. Which means we should immediately go to this and say, okay, I can move it. Okay, which then puts the positive charge up here. Now you'd ask yourself the exact same question. Okay, what is wrong with this structure? Well, it's a positive charge on a carbon. It's secondary. Oh crap, I hit a secondary carbon again. So try again. Now that puts the positive charge on this carbon. Okay, well again, carbon, and then we could kind of go secondary, but then say, well, our primary, secondary, tertiary was ultimately a way to look at stabilization of that positive charge. Is there something else present there that could stabilize that positive charge? Say like lone pairs on that bromine. Okay. So if we go through and evaluate, it's secondary, secondary, and then secondary plus bromine. Well, that plus bromine, that bromine has electron density that it could use to stabilize it. That's my best structure. Okay. So find the thing that makes it bad, fix it.
So even though the bromine is electronegative and would withdraw electrons, it could still theoretically
Yes.
stabilize it.
Yep. So if you see lone pairs next to it, resonance can happen to stabilize it.
So between the Br and the NO2, the Br is better.
I don't know what you mean by better.
Like what if the plus sign you move it to the NO2?
So with this structure, the way it started, could we move the plus sign to the NO2? It's not physically possible. Okay.
Oh, yeah.
So, and that's something that they could easily do. Maybe they started you off with, we erase all of that. Maybe they gave you this structure. Said, okay, we're going to make, where did I put the bromine? I didn't put it there, did I? We're going to make this structure. Which of the following are valid resonance structures? And one of the structures they give you is that. Okay, that's going to be a pretty tricky one because you could go through and draw resonance all the way around that. Okay, if you knew the Lewis structure for NO2, that might help you out and trigger that that's really bad. Okay. But if you don't know the Lewis structure on NO2, that gets a little bit trickier to deal with. So what might be helpful to go through and do is draw in atoms that are missing. When we look at that structure, are there missing hydrogens? Okay, we have to make sure our carbons all have their octets. If we go through and do the same thing with our starting material, should have drawn them in red in the first case. Is there anything that's majorly an issue with this? How the heck did that hydrogen get onto that carbon? Not only did we put on the nitro, but we somehow jumped a hydrogen to a different position. Okay? There wasn't a hydrogen there originally, and if we take a look at our product, there still isn't. Okay? The intermediate that they've showed here doesn't make physical sense for the reaction that they asked for. Okay? So a lot of times if you draw in the hydrogens, it can help you see that what's wrong with the structure. If you don't draw in the hydrogens, sometimes you see it, sometimes you don't. Okay? Other questions? Okay, I do briefly want to talk about radicals, and it will be very, very brief. Let's see, what did I put on the next slide? Radicals. What is a radical? Shoot. Okay. A radical is a carbon, or really any atom with just one electron. Okay, so there's a radical. How should we treat radicals? What makes radicals reactive?
They want another.
They're missing an electron. What other structure or what other type of carbon is missing an electron or missing electrons?
Negatively charged or positively charged?
Positively charged. Radicals are effectively the same as carbocations. So where do we want a carbocation? Primary, secondary, tertiary? Tertiary. Where do we want a radical? Tertiary. Treat it exactly the same. You should be okay with those kind of answers. Okay? Where you'll run into some kind of trickier things, which is what you should have seen in first semester, would be kind of mechanism-specific things for radicals. Do I have steps on this? Not sure I really like that. So our initiation step, your initiations, things that are going to trigger your initiations, you're looking at light, heat, peroxides, so seeing that ROOR bond. Halogen bonds work just as well. Why would halogen bonds work just as well as a peroxide bond? What's that? It's the electronegativity difference. Okay? The oxygen-oxygen bond was highly reactive because oxygen's electronegative, it wants its electrons. Bromine is pretty reactive because bromine's electronegative, it wants its electrons. So all of those bonds have a weakness where we've attached two electronegative atoms next to each other. All of those are very willing to break in what is known as a homolytic cleavage. I think I did that right. Where the electrons go back to the original atoms that started with them. And we end up with a radical. So in our initiations, those are things to look for, and the product of an initiation reaction will be a radical, whereas the reactant won't, right? Because we initiated it. We started the radical reaction occurring. So if you're given a sequence of reaction and asked, tell me which one's a propagation step, or which of the following is not a propagation step, you need to know what the initiation, propagation, and terminations are. Your initiation, you make the radical. You do not start with one. What happens in the propagation? You start and end with a radical. What was that? Interesting idea. I don't know. I've never learned or heard an explanation for why they're diatomic. I can take a look for that. Yeah, and I'm not quite sure I accept that answer because if you look at lithium, lithium has one electron, or one valence electron. It's not diatomic. Oxygen has a whole lot more than one electron, valence electron, but it is diatomic. So, what happens in our termination reaction?
No longer have a radical.
Okay, we start with a radical and lose it or end with neutral. Product is neutral. Okay. When it comes with initiation reactions, there's pretty much one initiation mechanism. Okay? You form the radical, there aren't a whole lot of options. We could put in a whole bunch of different reagents, but ultimately you end with a radical, and you didn't start with it. For the propagation, there's a lot of different ways that you could end up with a radical at the end of a reaction, or at the end of a single step. There's a lot of ways that you could have started with one. So there's a lot of possible answers for a propagation. The terminations, while it may seem like there aren't a lot of ways, there are a lot of ways to generate your terminations as well. because you can terminate by gaining an electron from the reaction flask, from the wall, from something else, some other radical initiator. Right? So the initiation is probably one that you won't see a question on because it's fairly obvious. It's either an initiation or it's not. Okay? Other questions that you might see is which of these is a valid mechanistic step for a radical reaction. Those get a little bit trickier to deal with because you have to know more about the mechanism for how it occurs. When we're looking at our halogens, those are kind of nice because what we're going to do is start with a bromine radical, and then we're going to make a new radical. Okay? What's the first thing that that bromine is going to see, or that halogen is going to see? Hydrogen. It's the most external thing within that structure. So after our very first, once our initiation is started, our first propagation is going to be the formation of a carbon radical. We wouldn't form the hydrogen radical because how stable is a hydrogen radical? Not very stable. Okay? So what we're always trying to do is propagate that kind of stability all the way through that. Okay? When you go through and look at your alkenes, those react a little bit differently. Where's the first radical going to form? Should it be with a hydrogen?
No, attack the pi bond first.
Why does it attack the pi bond?
Those are the most available electrons.
The pi bond has the higher energy electrons. So when we have an alkene, we would expect our pi bond to react. So it's going to give up an electron to our halogen, and we're going to be left with an electron on our alkene structure. Where should that electron be left? Which carbon?
The secondary,
Why the secondary?
more stable.
More stable for our radical. Treat it like a carbocation. That's where we would expect it to show up. Okay? Other reagents you can see for these, NBS shows up as a radical formation. Why would we expect NBS to generate radicals?
Still using bromines.
It's not just that we're still using bromines. What's that bromine bound to?
Another electronegative band.
A very electronegative atom. Right, so again, we have that very weak bond because we've got two electronegative atoms pulling on those electrons. Okay? So NBS effectively is the same as Br2, right? Except it's how do you get that bromine into the solution. Okay? NBS gives you a very small amount of it, which means that it reacts with the first available thing. Your pi bond is higher energy, but is it going to be the first available? Hydrogens are probably going to be the first thing encountered. Okay? So if we give our reaction enough time, we would expect the pi bond to react because we got a ton of things going on. If we don't give it that time and we're looking solely at the very first thing possible, NBS is going to start to push reacting with hydrogens, but they need to be reactive hydrogens. Those reactive hydrogens will be your allylic position. Why would those reactive, or why is that position more reactive than any other? What happens if I turn that carbon into a radical? Conjugation works. We have conjugation with the pi bond or resonance with the pi bond to stabilize it. That ends up being our more reactive position. Okay? So you can expect to see a few radical reactions probably show up. My guess would be one or two, probably not a lot more than that. Yes?
So I think they were showing yield, the first one, the first step.
So
Should we worry about that?
when we're looking at radical reactions, most of them are with bromine, and that is because bromine is selective. Chlorine is not very selective, and that's what they're, what that 50-50 is saying. Chlorine tends to react with whatever it can find, whenever it can find it. So we don't get specificity in the reaction. Remember, why are we doing experiments? To make one product. If we've got the potential to make 50 products really well, okay, well that's great, but then my yield for each of those products becomes really piss poor. I don't want to deal with that. Okay? So you will typically see bromine involved in your radical reactions. Chlorine can show up, it's just not quite as common. Okay? Substitution. So yay, the 30 minutes ago I said this is what I want to talk about. I didn't talk about it. So our substitution reactions. This slide I think is very helpful because it identifies all the individual pieces within the substitution reaction. Whether we're looking at SN1 or SN2, it's all about a balance of what is happening or how each of these things is happening. So we're always looking at these four possible things and how each of those things pushes one mechanism over another. Okay? So this very last statement down here is really asking what must occur. For this reaction to occur, what do we have to do?
Leaving group leaves, nuclear final attacks.
We have to break the bond with the leaving group, and we have to make the bond with the nucleophile. That's it. Two things. Right? The order that those two things happen in is how we get our SN1 or our SN2 reactions. Right? When it comes to those, this is, I think, really, really important to memorize. Right? Primarily, I would say right here, SN1 means stable carbocation. Right? At the end of the ACS test, I expect you to remember your name and that statement. SN1 equals stable carbocation. Right? Because that's going to drive a lot of your reactions. SN2, you get two things to remember because it's SN2, right? There we go. Steric hindrance and a good nucleophile. Those are critical to the SN2 reaction happening. Everything after on those lists is derived from those two statements. Everything. Right? A lot of people have asked about solvent effects. Well, the solvent goes back to what has to happen. In the SN1, we need a stable carbocation. The more stable the carbocation, the more likely the SN1 reaction occurs. How can I stabilize a carbocation? Give it something negative. Right? The solvent can bring in partial negative and partial positive. The more negative the solvent is, the more stable it can make that carbocation. The best way to get a negative solvent, a protic solvent, because it wants to get rid of the proton, H+, which means what's left on the solvent.
Negative charge.
A negative charge, which can be used to stabilize the cation. If we look at the opposite, an SN2 reaction, what we're concerned about is a strong nucleophile. What makes it a strong nucleophile? Negative charge. If I use a protic solvent, I've got H+. What happens when I bring that plus near that negative nucleophile? Neutralizes it, and I no longer have a strong nucleophile. I need a strong nucleophile for an SN2, so a protic solvent is an awful choice. Okay? So whenever you come across these types of reactions, look at what they've provided you. Look at the substrate, look at the leaving group, look at the solvent, look at the nucleophile, and try and quickly assess what do you have. Okay? With that information, you can decide where your mechanism should go. Once you know what mechanism you're dealing with, that can give you stereochemistry, that can give you the ability to predict those products. Okay? So it's really hugely important for understanding these. The ACS study guide asked some questions about rates. Not sure it's really worth you remembering that, but I will ask one quick question. What do the brackets mean?
Concentration.
Concentration. What are the units on concentration? Molarity. What are the units on molarity? Moles per liter. Does the solvent play an effect in this? Changes the molarity. So if I change the amount of solvent that's present, I change the rate of the reaction, even though the solvent doesn't show up officially in my rate. Right? It shows up by making the concentration different. It does have an effect on the mechanism or on the rate of the reaction. Okay? So there's sneaky ways that they can ask you these questions, and it ultimately comes back to really, really understanding what's happening within each of these reactions. Okay? Thankfully, we didn't get something that nitpicky this semester. But substitutions do hit you that hard. your eliminations, same general idea, try and figure out those patterns on what's happening between them, okay? So we're really breaking two bonds. I would argue that the formation of that pi bond is not really a mechanistic step because all that is a resonance structure. Positive on one, negative on the other. There's no pi bond in that case, okay? So the important aspect is breaking those bonds. How do we break those bonds? Okay? So it's going back, trying to identify the bare minimum of what is happening at each stage and doing whatever you've got to do to get that set up. And yes, that pushes different mechanisms. You end up running into the similar rules behind these. Okay? I do want to at least give you the heads up that that is officially time. I got no problems to keep on talking, but that is time. So if you got to go, you can take off. And you're more than welcome to take pizza with you too. Should I keep talking?
You're recording it, right?
Yes, it is being recorded.
Keep talking all day.
I don't think I'll go quite that far. Within each of the elimination mechanisms, you get the same results as well. Because it's getting noisy.